Bismillahirrahmanirrahim. Assalamu alaikum warahmatullahi wabarakatuh. So we are just discussing the exact differential equations, and as you know, we discussed in the last lecture the exact differential equation. Now this is our lecture 11, and we are going to discuss the equations which are not exact. We have the test for the exact differential equation. So that test is that partial m by partial y is equal to partial n by partial x. So if we are having here the case that partial m by partial y is not equal to partial n by partial x, the question is, sometime we can make the equation exact when we multiply our equation by integrating factor. So in this case, we will be studying in this lecture how to find the integrating factor for the differential equation which is not exact, and sometime we can make it exact. So we write integrating factor as if. So here we will write sometime as a function of x, or we write as a function of y. So we take the difference of these two. I take partial m by partial y minus partial n by partial x. I can find the difference that partial n by partial x minus partial n by partial y, or we write partial n by partial y and partial n by partial x. So this is my n, so I will divide by n, and if we can find factor 1 upon n partial n by partial y minus partial x, this is my is equal to f of x. Then I can define my integrating factor. My f of x is my integrating factor is equal to e to power integral f of x dx. So this is my number one. I can find the integrated factor as a function of x only, this function of x only, and this function of y only. Then the second case is the case that we have this I take as number one. And number two, I can get the integrating factor. I can just take the difference as I did before. I take now partial n by partial x and partial m by partial y. Here this is my n, I divide by 1 upon m. If it comes to be the function of y, the function of one variable, again I am saying this must come either function of x or function of y. If we are not going to get this one, it means we can't find the integrated factor, and we can't make an equation, exact differential equation, by multiplying integrated factor. If we get it, then we can make exact differential equation and we can solve it. Now here I find my integrating factor. If this is so, then I can write here my integrated factor g of y is equal to e to power integral g of y dy. So this is how we can find. This is my equation 2. So if I am given an equation, I have the integrated factor, I can apply that integrated factor, make the equation exact, and we can solve it. I'll give you the example for this purpose. We take an example. I show you that how to find the integrated factor and how to multiply to get it to be exact. Now we have the differential equation y dx plus 3x minus y dy. So I can define here my mxy is equal to y, and my nxy is equal to 3 plus 3x minus y. I write here partial m by partial x. We check is exact or not. Partial m by partial y is equal to 1, and partial n by partial x, this is equal to, this value is 0, this value is 0, because they are constant. We get the partial differentiation and derivative of this one with respect to x will be 3. So we have partial m by partial y is not equal to partial n by partial x. This implies the differential equation we are having, differential equation is not exact. We check if we can find, we can use number 1, number 2 to find the values as exact. So I just start from 1 upon n, this one. We take here, we try this one, 1 upon n into partial m by partial y minus partial n by partial x, and we can write here 1 upon n is equal to 1 over 3 plus 3x minus y, and this is partial m minus partial m by partial y minus partial n by partial x is 1 minus 2. We get here minus 1 over 3 plus 3x minus y, and this is not a function of x. We can see it here. This is a function of x and y. So it's not possible to use this formula to find the integrating factor, because here we can find it only it's coming to be function of x. It means we are not able to use this one. We use number 2. We use number 2, and we can see it here. We use number 2, and we can have here 1 upon m. 1 upon y. What's my m? My m is y. 1 upon y. I just rewrite it. We are having here we have 1 upon m into partial n by partial x minus partial m by partial y is equal to 1 upon y, and with 3 minus 1, we get here 2 upon y. And this we get here function of y only. This means we can apply this formula number 2 to write our integrated factor. We can write here gy is equal to e to power integral 2 upon y dy. This is equal to e to power 2 dy upon y is equal to e to power 2 ln of y is equal to e to power ln of y to power 2, and we can have here this is equal to y square. E and ln are cancelled. We get this is equal to y square. So our integrated factor g of y, that's equal to y square, and you can use this integrated factor. We just, as I told, we take our differential equation. This is my differential equation. I multiply this differential equation by integrated factor, both the sides. So I can get here the new integrated factor is y square. We multiply this one, and we get here y into dx plus y square, and we having here 3 plus 3x minus y dy equal to 0. Multiplying here, we get here y cube dx plus 3y square plus 3x y square minus y cube dy equal to 0. So I take my new nxy, mxy is equal to y cube, and my new nxy for the new equation is equal to 3y square plus 3xy square minus y cube. So these are my modified form of my m and n. Now I check, can we find here our test for the exactness? If this is exact, then we can solve by the method of exact differential equation. So I find here partial m by partial y is equal to 3y square, and find partial n by partial x is equal to derivative of this one is 0, y is constant, derivative x is 1, we get here 3y square, and this implies partial m by partial y is equal to partial n by partial x. This I take as my equation number 3. So I say my equation 3, the differential equation, is exact. The differential equation is exact. Now we can apply our method for finding the solution. We get here partial f by partial x is equal to mxy, and that is my mxy is y cube, and I am having here partial f by partial y is equal to nxy is 3y square plus 3xy square minus y cube. So I say this is my equation number 4, and this is my equation number 5. So as I told in the method, we can take number 4 and partially integrate with respect to x, or we take number 5 and partially integrate with respect to y. Both ways the result will be the same. So I just take the first one and integrate with respect to x. So I get here fxy is equal to integral y cube dx plus, because we are integrating with respect to x, so our constant will be with respect to y. We get here gy. So my solution will be fxy is equal to xy cube plus gy. So I say this is my number 6. So I have here, you can see, we are having here, I will not use number 5. So now we take number 5 here. I get the value from this one of partial f by partial y and substitute in number 5. So I take the partial derivative of number 6 with respect to y. I get here partial f by partial y is equal to, with respect to y, we get 3xy square, plus this is function of one variable only, function of y, so write here dg by dy. This my equation will be equation number 7. So now we are having here number 5 and number 7. So we substitute this from equation 5 and equation 7, I substitute the value of dy by dx, a partial of partial y there. I'll get here 3xy square plus dg by dy is equal to, but to the right hand side, there is 3y square plus 3xy square minus y cube. Now there is some cancellation, so this factor of partial f by 3xy square is cancelled with 3xy square, and what's left? We're left with here dg by dy is equal to 3y square minus y cube. We integrate this one with respect to y. We get here gy on the left hand side, and right hand side we have the integration 3y square minus y cube into dy. And we integrate this one, we get here 3y square y cube by y cube by 3 is cancelled. We get here y4 by 4 plus one constant. I'm just keeping constant with me. I just tell you why. So we want to find the solution. We substitute this one in equation number 6. Substituting in 6, this one substituting in equation 6, we'll get here fxy is equal to 3xy cube plus y cube minus y4 by 4, and here I write this equal to constant. If I write here C1, again I put a constant, then we combine this one as we did in the exact equation form, but we know this our solution of this one is this here df, and fxy is equal to C is its solution. This is my df. So we can write here our solution is solution of differential equation, or general solution it is. The general solution of the differential equation is x y cube plus y cube minus y to power 4 over 4 is equal to constant. See, this is explicit solution.